Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today we will discuss about engineering typology subject. Already we have discussed various parameters involved in engineering typology like friction and wear and lubrication importance in tribology, and we are discussing the question bank related to these modules. So now today we will see question bank of corrosion, the long answer type of the questions we will discuss in this session. So in this, the topic is question bank of corrosion. So already we have seen a definition and terminology and short answer type questions also we have discussed. But in this session, we will learn how to attempt the for long answer type questions in the examination. So they will ask sometimes the questions like this. They describe briefly about electrochemical theory of corrosion. So in this, how to describe about electrochemical theory, whatever you learned in a theory part. This type of corrosion occurs where a conducting liquid is in contact with the metal. So this corrosion occurring where a conducting liquid is in contact with the metal only. So that's why this corrosion, this type of corrosion is the electrochemical type of corrosion. Already you know the non-electrochemical and electrochemical corrosions are there. So this corrosion occurs due to the existence of separate anodic and cathodic parts. So anodic and cathodic parts they will separate, between which current flows through the conducting solution. So whenever the current is passes through this conducting solution, they will separate. At anodic area, oxidation reaction occurs, thereby destroying the anodic metal either by dissolution or formation of compounds. So hence, corrosion always occurs at anodic parts only, which the corrosion undergoes the anodic only. The cathodic is uncorroded part. So the mechanism of wet corrosion. So here electrochemical corrosion involves the flow of electrons between anode and cathode. Already we have discussed in the definition terminology. The anodic reaction involves dissolution of metal liberating free electrons. So the equation here shown. The anodic reaction involves solution, the metallic anodic reaction here shown. The n plus 1 and n E minus. So electron, the dissolution of metal liberating the free electrons here. Free electrons are shown here, n E minus. So the cathodic reaction consumes electrons with either evaluation of hydrogen or absorption of oxygen, which depends on the nature of the corrosive environment. So this is evaluation of hydrogen diagram. So this type of corrosion occurs in acidic medium. So example, considering the metal that is Fe in a acid solution, anodic reaction is a dissolution of iron as ferrous ions with the liberation of electrons. So in this diagram shown here, iron metal and anodic area is large and the Fe anodic area large. This is a ferrous anodic area and a small cathodic compound part and acidic solution and diffusion. You can see in this the diagram how they are dissolution of iron as ferrous ions. So that anode, the reaction is the ferrous Fe2 plus and 2E oxidation occurs. The electrons released flow through the metal from anode to cathode, whereas H plus ions of acidic solution are eliminated as hydrogen gas. So at cathode 2H plus 2 hydrogen atoms plus 2E, 2 electrons, it gives reduction. So the overall reaction is Fe plus 2H plus, it It gives Fe2 plus electrons plus H2. So this type of corrosion causes the displacement of hydrogen ions from the solution by metal ions. So the all metals above hydrogen in electrochemical series have a tendency to get dissolved in acidic solution with simultaneous evaluation of H2 gas. The anodes are large areas, whereas cathodes are small areas. So note this point. The anodes are always large areas. So electron transfers from anode to cathode. The corroded part will be occur at the anode. So absorption of oxygen. For example, rusting of iron in a neutral aqueous solution of electrolytes in presence of atmospheric oxygen. Usually the surface of iron is coated with a thin film of iron oxide. If the film develops cracks, anodic areas are created on the surface. So while the metal parts acts as cathodes, it shows that anodes are small areas, while the rest metallic part forms large cathodes. So the released electrons flow from anode to cathode through iron metal. So this is the theory behind this absorption of oxygen. So you can see in this the diagram the absorption of oxygen. The small anodic area shown here produced by cracks in oxide film. The reaction already shown in previous slide. The ferrous 2 plus 2 electrons reduction, and then the cathode and the cathode large. Set anode oxidation will be occurred at cathode reduction. The reduction equation shown in this slide. The overall reaction is Fe2 plus 2OH minus. So it gives ferrous hydroxide. So if oxygen in excess, the ferrous hydroxide is easily oxidized to ferric hydroxide. So equation shown in this, the rust formation will be occurred like this 2Fe2O3 under 3H2. The rust formation. So if the oxygen is in excess, the ferrous oxide hydroxide is easily oxidized to ferric hydroxide. So next question, briefly explain Curvey's corrosion with suitable diagram. So the Curvey's corrosion is a localized form of corrosion that occurs in confined spaces or curvaces where the environment differs significantly from the surrounding open surfaces. This type of corrosion is common in metals and alloys, particularly stainless steels, and is often seen in areas where two surfaces are in close proximity, such as under gaskets, seals, washers, lap joints, and fasteners. So Curvey's corrosion generally occur so wherever the close proximity is available, like gaskets and washers and joints, lap joints and fasteners, rivets, bolt and nuts. So all these types occurred the Curvey's corrosion. So the mechanism of Curvey's corrosion is, one is initial condition. At initial condition, the metal surface is exposed to a corrosive environment. The entire surface may initially corroded uniformly. The oxygen depletion in the curvaceous area the oxygen is consumed faster than it can be replenished. So leading to oxygen depletion. So the metal surface is exposed to corrosion environment. So the entire surface, whenever the metal surface exposed to environment, that entire surface may initially corroded. And the uniformly corrosion will be possible. Whereas in oxygen depletion, the oxygen is very faster than can be replenished. So change in chemistry. The difference in oxygen concentration between the inside of the curvace and the outside leads to a change in the electrochemical potential. This causes the metal inside the curvace to become anodic, that is more reactive compared to the surrounding area, which becomes cathodic. Next, fourth point, acidification and chloride accumulation. As the metal inside the curvace corrodes, metal ions are released, which can hydrolyze and produce acidic conditions. Additionally, chloride ions can become concentrated within the curvace, further accelerating the corrosion process. The propagation. The anodic reaction within the curvace leads to more metal dissolution, while the cathodic reaction outside the curvace is often the oxygen reduction. So, in the case of acidification and chloride accumulation, what happened? The metal inside the curvace corrodes, metal ions are released. So here, in the case of propagation, the anodic reaction within the curvace leads to more metal dissolution, with the cathodic reaction outside the curvace is often oxygen reduction. This process can cause severe fitting and structural damage over time. So even if bulk material is generally resistant to corrosion. So overall, the structural damage will be occurred even if it is in general resistance to the corrosion. The curvace corrosion diagram you can see. So in this curvace corrosion, what happened? Whenever the object is subjected to exposure to the environment, that is air. So the O2, when reaction with O2, what will happen? The passive film occurred here, ferrous hydroxide, and then one shield, the protective shield also formed. So here, the ions are separated here, Na plus and Cl minus, chlorine, and like this. To explain pitting corrosion. So the pitting corrosion is due to crack on the surface of a metal. There is a formation of a local galvanic cell. Local galvanic cell means pinholes, feeds, and cavities in the metal. So this corrosion will be occurred on the metal surface due to the crack, the small crack on the surface. It leads to fitting corrosion. The fitting is usually the result of the breakdown or cracking of the protective film on a metal at specific points. This gives rise to the formation of small anodic and large cathodic areas. In the corrosive environment, this produces corrosion current. So the diagram you can see the corrosion product and more oxygenated cathode reaction and more oxygenated cathode reactions you can see in this diagram. So here anode is attacked. The attacked component part is anode. So this is iron surface. So here the pitting corrosion occurred in this crack, pits or cavities. So the anode reaction already we have discussed in previous slides. Oxidation reaction and then reduction. So the overall reaction, ferrous hydroxide easily oxidized to ferric hydroxide. So the product called the yellow rust corresponds to the Fe2O3 3H2O, the ferric hydroxide. Next question is explain the process of waterline corrosion. So what is this waterline corrosion? This is also known as differential oxygen concentration corrosion. It has been observed in the case of iron tank containing water that the portion of iron tank just below the water level undergoes corrosion. It is due to the difference in oxygen concentration. So the area above the waterline, highly oxygenated, acts as cathodic and is not affected by corrosion. However, if the water is relatively free from acidity, little corrosion occurs. So this type of corrosion is prevented to a great extent by painting the sides of the ships by anti-fouling paints in marine applications. So the differential oxygen concentration means due to the difference in the oxygen concentration. So above the waterline are highly oxygenated, not affected by the corrosion. So below the waterline, a very low oxygenated formation will be happen. So this type of corrosion is prevented to a great extent by that painting the sides of the ships by anti-fouling paints. So the waterline corrosion, so you can see in this, the poor oxygenated acidic part is corroded. So in this below the waterline. So the above the waterline highly oxygenated, the cathodic part, this one is protected. One is unprotected and another one is protected. So the waterline corrosion at anode equation, oxidation equation, at cathode reduction, and overall reaction you can see if oxygen is in excess, the ferrous hydroxide is easily oxidized to ferric hydroxide. So the product called yellow rust, that is corresponds to Fe2O3 and 3H2. Next question, discuss the general corrosion prevention methods. The corrosion control methods. So what are the how many prevention methods are there to control the corrosion? So one is electrochemical protection or cathodic protection. The principle involved in the electrochemical protection or cathodic protection is to force the metal to behave like a cathode. So already we have studied in theory part. In this, the electrochemical protection or cathode protection, so the metal to behave like a cathode. So there are two types of cathodic protection. One is sacrificial anodic protection, another one is impressed current cathodic protection. So what is this sacrificial anodic protection? So here you can see in this diagram shown the sacrificial anodic protection. In this method, the metallic structure is to be protected to behave like a cathode by connecting it with more active metal. So there, the connected metal here, sacrificial anode oxidation, Mg magnesium and a ferrous pipeline cathode. That is reduction. So here, so that the corrosion will concentrate only on the active metal. The artificially made anode thus gradually gets corroded, protecting the original metallic surface. So hence this process is otherwise known as sacrificial anodic protection. So aluminum, zinc and magnesium are used as sacrificial anode. So in this diagram you can see the magnesium is used as an anode, connecting it with more active metal, that is anodic metal. Another one is pipeline. The cathodic material is pipeline. Which metal have to protect from the corrosion, so that this type of corrosion will concentrate only on the active metal. So you can see the protection applications. The important application of these methods are protection of underground cables and pipelines from soil corrosion. You can prevent. And in marines, the important application of this method, protection of ships and boat hulls from marine corrosion. So boat hulls you can prevent from this type of corrosion. So one is sacrificial protection and protector. The important application of these methods are the prevention of rusty water by inserting magnesium sheets or rods into domestic water boilers or tanks. Inserting magnesium sheets or rods, so you can see in this diagram, into domestic water or the domestic water like applications, boilers and tanks. Next, impressed current cathodic protection. In this method, the impressed current is applied in the opposite direction of the corrosion current to nullify it, and the corroding metal is converted from anode to cathode. This can be done by connecting negative terminal of the battery to the metallic structure to be protected, and the positive terminal of the battery is connected to an inert anode. So this impressed current cathodic protection can be done by connecting the negative terminal of the battery to the metallic structure, which part you are going to be protected. So inert anodes used for this purpose are graphite platinized titanium. So in this the source of current shown anode and cathode, they are connected to the pipeline, the insulated copper wire and the soil and black pill and graphite anode. The purpose to graphite platinized titanium. The current is applied in the opposite direction of the corrosion current. So the anode is buried in a backfill containing mixture of gypsum, coke, breeze, sodium sulfate. The backfill provides a good electrical contact to anode. The applications are structures like tanks, pipelines, transmission line towers, underground water pipelines, oil lines, ships, etc. etc. can be protected this method. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.